Texas Lutheran University.
I just wanted to make sure, Jesus.
Well, it is our great pleasure and honor, and I guess that's all I got, right? To introduce Eddie Scott, who's been here for, what, 7.5 years?
Basically?
7.5 years, right?
Yeah, a long time.
Eddie's graduating with a BS in chemistry, perhaps, maybe.
Maybe.
And he's gonna head back to Beaumont,
Yeah.
right? And eventually go to grad school, or I'm gonna come to Beaumont and find him. Right?
That's the plan.
Inorganic, right?
Yeah.
Yes.
Yeah.
Trust me, that's in here.
Plus it does. And Eddie's going to talk to us a little bit about ionic liquids, how they work, the thermodynamics of them, and some current and new applications.
Thank you. As Dr. Davis said, my name is Eddie Scott here. If you don't know me, shame on you, but if you do know me, props to you. So I'll be discussing understanding thermodynamic properties of ionic liquids in regards to current and new applications. So a quick little outline, I'll be discussing what ionic liquids are, starting with kind of like a definition in general, moving into some history, and then some of the general properties. And after those properties, I can talk about the thermodynamic properties of ionic liquids. Once I finish with those, towards the end, I'll discuss the current applications and some brief future applications. So ionic liquids, what are they? They're basically salts that are liquid at room temperature, and that temperature is usually around 100 degrees Celsius, 212 degrees Fahrenheit, whatever pleases you more. And they don't really stay in 100 degrees Celsius range. They can vary to lower. Some values are negative, negative 50, negative 60 degrees Celsius, and some are higher, generally peaking at 600, 700, and 800. So ionic liquids are compounds completely made up of ions. So you have a cation, which is positive, and you have an anion, which is negative. And just a simple version, you have sodium chloride, sodium bromide, or lithium iodide. Any of the simple ones discussed throughout this presentation will show up. And so ionic liquids are polar, but they also have non-coordinating ions, which means the anion doesn't react or interact well with the cation whatsoever. And that's due to the size of the anion and the asymmetrical abilities of the cation. So what happens, you have a delocalized charge, which is one component, and also an organic component. So what happens is the electron is not attached to any bonds, but it has the ability to step out of the boundaries of the Lewis structure. And this is an interesting situation. So in order to kind of study that more, you use resonance structures. I don't know, all of you have done resonance structures multiple times. Maybe, yeah, resonance structures. Okay, so through those, you can actually study and record the location of the electron. And so ionic liquids also don't have stable crystal lattices. And a crystal lattice in water, we'll say, is very stable. There's no defects, meaning that there is no ion flowing around. There's no charge moving around freely. And so with ionic liquids, that what makes them unique, because the stoichiometric properties aren't 1-to-1. The ratio is usually 2-to-1, maybe 4-to-1. That's due to the size of the anion and the asymmetrical abilities of the cation. And so here are some names. You have the most common ones, which I'll use quite a bit: ionic liquids, IOs, and room temperature ionic liquids, RTILs. And then one that's kind of used quite a bit are these right here, molten salts. And they deal with liquids that are kind of the 600, 700, 800 range. So we talk about the sodium chlorides, sodium bromides, and stuff like that. You also have room temperature molten salts, liquid organic salts, fused salts, and neoteric solvents. So here, I want you to focus mainly on the first several here. So I think the 1-ethyl through 1-hexyl, the 1-ethyl 3-methyl imidazolium cations, those are more important because of their chain length, which is very important, and also because they're melting points. You'll see some, they use the pyridinium, but it's not as important or not used as much for the cations. And then also anions, there's a lot of bromide, iodide, chloride, methyl sulfate, and then tetrafluoroborate is used quite a bit. So now moving on to some history. In the mid-1800s, around like 1860, the first ionic liquid was discovered as a red oil in Friedel-Crafts reaction. And for y'all who don't know Charles Friedel and James Kraft, you're losing in life. But basically what happens is they came up with a process where they would take a CH atom off of an aromatic ring group and replace it with an alkyl halide. And in the process they would use a catalyst, which this is where these ionic liquids come in handy. So they came up with an aluminum chloride derivative. So they used here, as you can tell, heptachloride dialuminate salt. And it proved to be extremely useful. It was useful in the fact that since they didn't know much about the physical or chemical properties, they weren't really able to understand that because the NMR wasn't invented yet. And NMR was invented around 1950, I believe. So what they just used it for is kind of useful material. They couldn't really improve on other applications. So around 1860s, this was kind of an important finding. It kind of was a pivot point to organic chemistry. Moving on to early 1900s, so they were able to synthesize the first room temperature ionic liquid, an alkylammonium nitrate. In 1914, so they decided to figure out, okay, this is where they start using chain links. This is one of the derivatives, so we have ethyl ammonium nitrate. You can see here, you can see the cation and anion, but it had the ability to have a melting point of 12 degrees Celsius, which is extremely important, because if you look back at molten salts, they had a melting point that was extremely high, and this works to be more beneficial in working as a catalyst in reactions. So the idea was keep the anions large, cations asymmetrical. And so 1960s, a man by the name of Lau A. King of the Air Force Academy, he had a group of researchers and students that were there on the base with him, and he decided to improve on using electrolytes and thermal batteries. And it's important, I put an asterisk here to kind of make a highlight, because in a world where you use energy a lot, and the idea of storing energy, it's very important that this idea was kind of used. So they wanted to figure out a way to improve on the electrolytes used in this eutectic mixture. So they had lithium chloride and potassium chloride. And the idea was to decrease the melting point while kind of keeping a high thermal stability. So after understanding the batteries needed to operate at a temperature of 375 to 550 degrees Celsius, they investigated those chloroaluminates that I discussed previously, and they were like, okay, let's figure out if we can use ionic liquids and see if we can decrease the amount of temperature needed for these batteries to kind of perform. They were able to do that. They came up with a structure that was able to reduce the temperature by 200 degrees Celsius. About 175 degrees Celsius is where they could operate now. And that's kind of important to see now, because there were plenty of prototypes created. And once those prototypes were introduced to the thermal battery industry, they were able to improve it, and they still improve it today. So that's very important. I want you to remember this. Moving along to 1990s, where most of us were born. All of us were born there except for 4 people. So discovery of ionic liquids that did not react with water. It's important because when dealing with those thermal batteries, a lot of times they would react with water, and they were like, okay, we need to kind of fix this. It doesn't pose a real threat, but it kind of hindered the ability for those applications to improve. And so they had to get away from the chloroaluminates, and they discovered these alkyl-imidazolium ionic liquids. And so after they were introduced, they kind of had a very good melting point, very average, good for what their structure was, and they had to use anions that kind of were fairly large in size. So they came up with tetrafluoroborate, and you have the hexafluoroborate. These weren't used too much. I see a lot of these because these deal a lot with viscosity as well. And later they came up with triflates, mesolates, and this other structure as well. So now properties. What are the ionic liquid properties? And these are extremely important because they have probably the most unique properties out of any liquid. Starting with great solvents for inorganic and organic materials, organic carbon chain based, and inorganic everything else. Non-flammability. There are times where they can be flammable, but there's not too many cases, so they kind of keep it as non-flammable, because most oftentimes they use those who have low melting points and work well with engines as lubricants and additives. Varying miscibility, their ability to act as a solvent. We use that in organic chemistry, and again for engines, they act as lubricants and any type of additive. Their ability to be stored for long periods of time without decomposition, and that mainly, this ties in with the thermal stability, because they have very high thermal stability, so they have the ability to stay at a high temperature range and not decompose as quickly as other solvents being used. And I will discuss this more when we get to applications with engines. Negligible vapor pressure, dissolution, recycles very easily, and extremely high ionic conductivity. And the ion conductivity happens from that defect in the lattice. The ion has the ability to free roam, especially when given the temperature difference. If you have a high temperature, there's more collisions, which the free roam isn't there. But with a lower temperature, there's more free roam, which helps with the ion conductivity. So here's just a chart. You can look at the values. Viscosity here, we look a lot at, and then conductivity, usually less than 10 millisiemens per centimeter. It kind of stops. The lowest value, I think, is 1.0 millisiemens per centimeter, which is really good, very conductive. And then vapor pressure, usually negligible. So moving on to high ionic conductivity. Like we know with water, water is conductive. I took my thing off on accident. But also we want to use ionic liquids because they have stronger ionic composition. So we came up with these values of 1 to values of 1 to 10 millisiemens per centimeter, and then they were able to understand those properties and create something that had 20 millisiemens per centimeter, which is extremely high, very conductive, which works well with a lot of reactions. So you have these two compounds here. You have the 1-ethyl-3-methyl imidazolium thiocyanate and the 1-ethyl-3-methyl imidazolium diacyanamide right here. So looking at this circuit here, you can see how the electrolyte works, and we need to understand the conductivity is directly related with the temperature. As I discussed previously, a decrease in temperature helps tremendously because in that lattice you have a couple defects, the Schottky defect and the Frenkel defect, and that gives the ion the ability to free roam. And so if you look at this next picture here, for the Schottky defect, you have two oppositely charged ions, and they have the ability to leave their site vacant and roam around the lattice. Over on the right side, you have the Frenkel defect, which a single ion, regardless positive or negative, has the ability to leave its site, and it will end up leaving it vacant, not being replaced by anything, and go to another site that's already being occupied and kind of move around in that area. So now moving on to dissolution. This is the ability for it to dissolve any application, any substance. So they use this a lot for cellulose. And the idea with cellulose, it's extremely abundant. I don't know if there's biology people in here, but okay, there's 3, 4. But the idea is that it's extremely abundant and it's used with a lot of applications. So trying to improve that a little bit better is why they use ionic liquids. Because I know with cellulose, if it were to be dissolved in something else, it'll actually swell up and it doesn't actually serve its purpose whatsoever. So for this idea, for its property, they wanted to kind of compare like, okay, what works best? Is it the cation? Is it the anion? Which serves the purpose of dissolution? So they used the 1-butyl-3-methyl imidazolium cation. They wanted to test that with several anions. So first they used normal ones. So you got the chloride, the fluoride, bromide, and iodide. But the issue was the viscosity increased tremendously, and that poses a real threat because it doesn't work as how it should be. It doesn't dissolve the substance as well as it possibly could. So they used different ions. So they tested acetate, formate, and phosphate. And you can see this value right here, 23 grams per mole of solubility, which is extremely impressive. And so they're like, okay, cool. So the anion obviously plays a role. So let's move on to the cation. Let's see if the cation kind of has more of an effect. So due to the chain length, they changed it up a little bit. They used the 1-methoxy-ethyl-3-methyl imidazolium, and that changed it by a factor of 3. So you have 8 grams per mole of solubility, which is a huge decrease. So we're like, okay, obviously they both play a role. So we need to understand that not only is the alkyl chain group important, but we also need to worry about the size of the anion. Moving on to present day, just like with the thermal batteries, the idea of having mixtures of ionic liquids poses to be more of a support system than doing it by itself. So they came up with weight percentages of 14.5 of 1-alkyl-3-methyl imidazolium chloride, and then a 16 weight percentage of the 1-ethyl-3-methyl imidazolium acetate. And it increases the solvent power using these two together, which also can be improved with dimethyl sulfoxide, DMSO, and it also reduces the reaction time, which is something that we look forward to when running experiments. So here's just a quick picture of applications used a lot for fuel. I know in clothing, maybe even shelters and stuff like that. So cellulose is widely used. Now moving on to negligible vapor pressure. And this is the idea of not having the ability to be volatile. We don't want to use liquids that are volatile. We don't want them evaporating into the air, and we don't want any fumes to be created. So using these ionic liquids, I first want to point out these. There are ionic liquids, they use IFS here, but I'm going to call these molten salts, that have a melting point of 800 plus, we'll say here. They actually have vapor pressure above 1 Pascal. So we can kind of count those out already. But when we compare these that are kind of on the lower trend, we got 3 ionic liquids here at low melting points compared to the water and benzene. And I want to note here that it does increase with temperature, so that does make sense. As the temperature rises, so does the vapor pressure. But you want to kind of stay in this area. When in comparison of about 50 to maybe 100 degree difference in kelvins, we can use these ionic liquids and they'll have no vapor pressure, which is good for us because we don't want anything to be volatile. So the idea was to get rid of these conditions where we had to keep them in ultra-high vacuum conditions or under hoods and where they wouldn't react with air. So the idea of using these low melting point ionic liquids with very strong compositions was what we really wanted to do. So that's why negligible vapor pressure is an important property to ionic liquids. Here's a quick little picture, just no vapor pressure in comparison to vapor pressure. It helps a lot with factories, it helps a lot with engines and stuff like that because the heat of the engine will actually cause the liquids to kind of be more volatile, increases safety awareness. So ionic liquids are really good. This is a very important property for ionic liquids. Now moving on to thermodynamic properties, which we know is the idea of understanding heat and temperature in relation to work and energy. So understanding how that works, we can discuss heat capacity, which everybody should know who's taken Gen Chem 1 or 2. It's the idea of heat required to raise the temperature of 1 mole substance by 1 degree Celsius without a phase change. But when regards to thermodynamics, we want to understand the ratio of energy and that temperature. So that's extremely important. Also, glass transition temperature, melting temperature, which relates to that asymmetric ability of the cation. We want to keep the symmetry very low. Thermal decomposition again. We have enthalpy, entropy, density, and viscosity. So talking about thermal stability and decomposition, we want to use applications at very high temperatures at some point. So we want to find ionic liquids that work best at high thermal stability and which don't decompose readily at that point. And so some of the biomass dissolution liquids that we use are acetate-based, amino acid-based, and then really focusing on the alkyl-imidazolium-based ionic liquids because of their abilities, or because of their ability for the anion to not readily interact well with the cation. And so moving on to understanding the stability order, first thing we can understand is the coordinating nature. We talked about the defect in the lattice, and we discussed how the free range, or the ability for the free roam to happen. Also nucleophilicity, how strong the nucleophile is, hydrophilicity, kind of reaction time, and then focus more on these two right here, because these are used a lot more, as I discussed at the very beginning. And there's also tetraalkylammonium and piperidinium. So decomposition occurs for several reasons. The main ones we want to talk about is when the anion attacks the cation. We discussed how for ionic liquids we really want that anion to not interact well with the cation. We want to keep it as a large anion base and an asymmetrical cation. And also we want coordinating anions. So any reduction of the coordination ions, we don't want that at all. So prevent decomposition, we want to keep that thermal stability high. So moving on to viscosity. Lower viscosity is extremely important. We use this a lot with engines. We use it a lot with any type of lubricants. We use it a lot even in reactions as well, like we discussed with the cellulose. So for viscosity, the anions play an important role. You can see here, as I showed, the tetrafluoroborate and the hexafluoroborate are used and actually have a very big reason for why this is viscous. And so they're like, okay, we need to figure out cations now. So they compared the two, alkylammonium base and then the imidazolium base, and the imidazolium proved to be a little bit better in viscosity. It proved to be a lower viscosity, and that's what we need to use because of the chain length. And what happens with the chain length, if it ends up being longer, it has the ability to be tangled, and the viscosity will increase due to that tanglement, and it takes a little bit longer for it to get untangled. So we want to kind of keep the chains fairly short. Here's just a table of showing you from shortest to longest, dealing with lower to higher viscosities. These are used quite a bit, the 1-ethyl, 1-butyl, 1-hexyl. And now looking at this chart, I really want you to focus on this left one right here, because the other ones are in comparison of some that are fairly high. But they use this chart to discuss the viscosity. So you understand at room temperature, generally right here, you know the 1-ethyl version has a lower viscosity, so that's what we want. And then we can compare, okay, 1-butyl, 1-hexyl, 1-octyl. It all increases as the chain length increases. But as temperature increases, we can also see, okay, the viscosity will decrease. But in general, we kind of want to keep with the 1-ethyl, 1-butyl, because if we can start low viscosity and start with a low melting point, it proves to be more efficient than, okay, let me start it with this 1-octyl, but then I got to raise the temperature by like an extra 100 degrees. We prefer not to do that, but it is possible. So in comparison, we want to work with these ionic liquid groups and maybe even the 1-butyl groups as well. So now moving on to applications. Due to these properties that we discussed, we can use them as lubricants and additives, any type of separation. We have solvents, electrolytes, and the ones I'm going to focus more on are solvents and organic chemistry for you, lubricants and additives, and electrolytes. So as a lubricant and additive, we know when any motor vehicle, what happens is due to friction, there's about 15% of energy loss. And in order to prevent that, we use oils. You know, if you don't put oil in your car, you're probably going to run into some problems. So use oil. And the idea is maybe even combination of ionic liquids with that oil or using ionic liquids in general to replace that oil. So here are the properties we'll be focusing on. High thermal stability, negligible vapor pressure, you don't want any explosions, you don't want to drive down the road and explode, non-flammability and high flexibility. So looking at comparing high viscosity and lower viscosity. The idea was, okay, high viscosity is going to be great because you know it'll be better wear protection. It's going to sit in there, it's going to be in between the piston ring to cylinder contacts, it's going to slow it down, it's not going to rub as much, and it's going to be more efficient. But then we look at low viscosity, and the idea was better fuel economy. And so they were able to kind of compose some tests. They compared, due to better wear protection, thermal stability, and pressure to viscosity ratio, we looked at a couple oils and an ionic liquid. So you have Mobil 1 engine oil. Everyone probably uses that. Royal Purple engine oil. Never heard of this, but people probably use it. And then ionic liquid version 17. Right off the bat, you can see these three values. Decomposition temperature, extremely important. It's a factor by 200. And we all know when a vehicle is running, it gets extremely hot. So if the decomposition temperature is low at like 230, 260, it's going to decompose at a higher rate. It's going to decompose a lot quicker. So we want to use the ionic liquid here, which is at 472. Extremely efficient. And then moving on to the viscosities, as we discussed, the higher viscosity here, okay, better wear protection. But the couple slides ago where we showed the graph, higher viscosity also as the temperature increases has the ability to decrease tremendously. So it's only about 6 more after so long than the other two. So granted, you want to kind of look at these two versions, but then you want to come back to this decomposition temperature, and you want to keep that fairly high. So also as an additive, now this is where we want to understand adding an ionic liquid to an already solvent to use an additive for engines. And the idea was, okay, maybe if we add it to something else, maybe it will help a little bit more. And yeah, that proved to be right. So we have comparison of high viscosity oils here, which starts off better wear protection, but over time, you can tell the lower viscosity one proved to be better. So the question they asked was like, do we want something that's working better now, or do we want something to work better over time? Because this can help with future applications where maybe we can come up with straight ionic liquids that can be at lower viscosity that start off better and finish better than high viscosity oils. So now moving on, probably the best part of my presentation like ever made, organic reactions and catalysts. So we're going to deal with how they work as solvents and how they work as catalysts. So first with the applications we'll talk about with catalysts, discuss the use of them to promote by Lewis acids, take advantage of controlled acidity, RTILs as neutral solvents, task-specific ionic liquids as ligands and catalysts, and also the properties you really want to understand is their thermal stability, kind of water solubility, how readily they are to be recyclable, and melting points. So now looking at Friedel-Crafts again, we understand we can do the alkylation, acylation reactions. So with alkylation, we discuss the substitution of the CH atom group on that aromatic ring. We'll use benzene as an example here, and it's replaced with an alkyl halide group. For the acylation version, we replace it with a carboxylic acid, as shown here. And for these reactions, the ionic liquid really serves its purpose to be more efficient. Now that we have NMR, we can understand its thermodynamic properties. We can use it for other applications, which, right here, for ferrocene. And for those who don't know what ferrocene is, this is extremely important in the medicinal field. A, because it has plenty of derivatives used for any medicinal reason, but also for cancer research, this is widely used. And the idea is you have cyclopentadiene anions here, kind of sandwich the iron. And what happens is a regular solvent has the ability for both of them to react. It has the ability to give them good yields, but the ionic liquid forces it to interact with both of them. So it forces it to give a better yield, better products, and it forces both rings to react. So that's why they use ionic liquids in this type of situation. And as a solvent, I'm going to discuss these a little bit more, but you want to really look at their low viscosities and high thermal stability, low vapor pressure, great solvents for inorganic and organic materials, extremely high polarity because we want to keep the non-coordinating ions in check, immiscibility and then synthetic flexibility. So dealing with hydrogenation, this is the ability to produce a hydrocarbon, and we kind of want to keep that hydrocarbon bond to a single bond, not a double or triple. And this gives us the ability to come up with naproxen, which is an anti-inflammatory drug, non-steroidal, I believe, right? Biology people? Okay, cool. And then along with that, it helps with pain. So if you have, I don't know, burns, cuts, blisters, sores, whatnot, go ahead and pop you a couple of these bad boys and you'll feel amazing. But what happens with hydrogenation, you need to react a metal complex in an ionic liquid. And because of ionic liquid's ability to serve as dissolution, you can dissolve this into this ionic liquid and the reaction works perfectly. The idea that the metal serves its purpose has to be done through this ionic liquid. So that's why ionic liquids are used in hydrogenation. Now moving on to supercapacitors and batteries. It's the best right there, that battery life is what I'm about to explain to you. We need to get rid of that. Lithium-ion batteries. So just like with supercapacitors and batteries, they generally work the same way. You have stored energy. You ready? Are we good? Okay, cool. So they store energy, and then they have the ability to release that energy. But more readily, supercapacitors and ultracapacitors are used for that reason. They can store the energy, and at any moment, you can flip the switch, turn it on, and you can get that energy as much as you want. Batteries, however, they do store more, but over time they decompose. That's why they want to kind of come up with the idea of lithium-ion batteries. Powerhouse, Dr. Bray, lithium. Yahoo, yeah, awesome. Use it as rechargeable energy. So this is what we'll talk about right here. You can see this graph. You have two metal rods and use the ionic liquid for the ions. They have strong ionic composition, so we use the ions to create that energy. And there's a separator in the middle. This is where we kind of trap and we kind of hold on to that energy and we can release it, discharge it at any moment, which proves to be extremely useful. So lithium-ion batteries. We want to recharge batteries. We want to use that because in a world where we have energy and need energy to use like almost anything, this is where we want to be able to improve on being more efficient when conserving our energy. So using ionic liquids creates a chemical reaction in the middle, and this chemical reaction will go over a certain amount of time regarding on how strong it is, and you can collect and store that energy and then use it throughout its decomposition state. And with lithium ion, their idea was to be able to charge this, and if you can recharge it, it's reusable, so the recycling rate increases if we can keep the stability and decomposition to a low. So that's why we use ionic liquids as electrolytes for batteries and supercapacitors. So kind of some future applications. Mainly for these engine lubricants and fuel additives, we want to focus on kind of running more tests where they don't act as additives, but they act as their own ionic liquid structure. We want to kind of keep it to where maybe we don't have to add anything to it. We can keep it low viscosity, but it still proves to be better than high viscosity. Solvents, working as a catalyst, keep those chains very low. We want to improve on melting point always, improve on the strength, and electrolytes, biofuel cells, and also for those lithium-ion batteries. So in conclusion, we know ionic liquids are absolutely amazing. Green solvents, green media, they have great properties. They work well with absolutely everything. They're improving tremendously now because about 150 years ago, they were like, what is this? Like, I have no clue what this salt is. It tastes salty, it looks salty, it works salty, but now it works to be better than just being salty. And so future applications I discussed, and then viscosity, dissolution, and their thermal stability, I think, are the most important things we really need to understand for ionic liquids, because if we want to improve on any type of reaction, especially with cellulose, especially with batteries, we need to understand the viscosity, dissolution, and thermal stability. These are my 17 references, and there are no questions, because everybody understands.
Any student or
No, I said there's no questions.
or friends? Well, that's too bad.
What we're going to talk about
You're not in
now
charge here, unfortunately.
is how much is everyone going to miss me when I'm gone?
Student, family, friends, questions first? Then the beatdown begins after that.
Yeah, I know. I'm so fucked.
You need a microphone on it.
I'm just kidding. That didn't happen. I'm sorry. Can you edit that out?
One question from the audience, or we ask 10.
You're going to leave it in there?
Close session.
No, no one ask any questions. Just tell me how great I did.
Their questions aren't going to be as bad as ours.
That's what I'm saying.
That's okay. I already told you what's going to happen when you ask me questions. Did y'all enjoy it? Was it cool? Yeah, cool. Okay, awesome. Great. Okay, cool. I'll just shut my mouth then.
Chemistry question
Wait,
would be good, Andy.
I got them at Dillard.
I have a question. Can you go to your slide about the cellulose? Please.
Can you click the
As soon as he
thing?
finishes giving you the death stare.
You know, Becky, I don't know much about cellulose. So how about you educate me? Let's go. Let's find it. This one?
Or the picture.
What's the purpose of the dissolution of cellulose in chemistry?
I know, because, I mean, cellulose, if you were to mix it with, like, water, it'll, like, kind of swell up, and they don't want to do that. They want to be able to break it down and study it more, and then they can apply it for, like, I don't know, fuel they use a lot of times, but I don't know. I saw there was clothing. They said shelter a couple times, and I was like, okay, cool, I guess, you know, just understanding the properties
What
of
kind of fuel can you make from cellulose? I know I'm not
biofuel.
supposed to ask questions now. What kind of fuel can you make from cellulose?
I don't know. I know this talked about, like, dissolving wood.
Don't avoid the
so
question. What kind of fuel can you make from cellulose?
I don't know. Green fuel.
Okay, what kind?
I don't know. I really don't.
What's a fuel you can actually ingest? That's the fuel they're trying to make.
Okay, awesome.
Yeah.
Oh, you can make bombs with sucrose too.
No. What kind of fuel? He has the attention span of a 5-year-old.
I really don't know.
What kind of fuel?
I really
What
don't know.
organic compound can you ingest?
You're talking to someone who doesn't know organic chemistry.
Doesn't matter. I bet you everybody in here doesn't know organic chemistry, and they probably can.
All right, well, let's hear the answers, guys.
On your truck, what does it say?
Back in my truck.
Yeah. Oh, is his truck weird?
I don't know. What, it's older, I think. But what kind of, why do they grow a whole bunch of corn in the Midwest, other than eating it? What's another reason they use corn? What?
He's calling the mom hotline, she knows.
There you go. What? That's right. Your
Mom,
mother.
okay, thank you. He was going to say corn syrup.
Same. Yeah, that's plant matter. They're trying to figure out how to make.
Awesome,
plant
learn
matter.
something every day.
Yeah. That's what cellulose is, plant matter, right? Plant matter.
Awesome.
His mom, she got a degree.
Hey, let's go.
I think his mother just got his BS.
Hey, good.
He's been dealing with his BS for a long time.
Well, that's right. I set that one up for you. He told me for that one later, so.
Wow, tag team me, huh? That's cool.
Other questions? Mom can ask a question now. Obviously, she's got some chemistry background over there.
Yeah, she's a genius. We know that.
Skip the generation, did it?
Yeah, move to that one right there.
All right, well, let's thank Eddie one more time.
For more information, please visit tlu.edu.